So I have some echo here. I think it's fine now. Thank you for your introduction. I'm sorry that I cannot be with you in person. Would have loved to meet you all face to face. So today I want to talk a little bit about Solar System Internet and the European Space Agency, about the ESA vision related to SSI and some of the related ESA activities. I will then talk about the key technologies, which for us are optical communication, position navigation and timing, and of course, disruption-tolerant networking, where I will go a little bit more on the detail of the various activities we have in this area. Then I will introduce the ASSIGN initiative, Advancing Solar System Internet and Ground, where we have a program proposal for our upcoming Ministerial Council, and conclude with a brief summary.
Felix, quick comment. We are getting a little bit of choppiness. Maybe you can try shutting down your camera and keep going.
Yes.
Maybe we can get just the audio. Thank you.
So I hope it's better now.
It seems so, yeah.
Okay, great. So roughly 2 years ago, we had an interdirectorate working group at the agency to define ESA's Solar System Internet vision, which is quite encompassing. So the vision is to establish a European interoperable institutional and commercial infrastructure with an appropriate governance and operational concept for providing network-based radio frequency and optical communication and navigation services to institutional and commercial missions in the solar system based on recognized international standards and collaboration with international partners. So you see here that interoperability based on open standards is very important to us, as well as an option to include commercial and institutional partners in a common internet network. This Solar System Internet vision had quite some impact on ESA at the highest level. So recently we have released an ESA Strategy 2040, which defines overall 5 common objectives for the overall agency. And this identifies strategic actions related to Solar System Internet and defines disruption-tolerant networking as a key technology. More specifically, we also derived an ESA Technology Vision 2040, where we have a dedicated theme on Solar System Internet, navigation and communication technologies. And this will have a concrete impact on upcoming study activities, for example. Of course, Solar System Internet, it's not only an ESA vision, it's a global vision. And here really the work being done in the last 2 decades on Solar System Internet in the various bodies like IUEG, CCSDS, IETF, and IPNSIC have been very instrumental in even getting this topic on the agenda of the agency, especially the IPNSIC reports received attention really at the highest management levels. We have various activities which can contribute and will contribute to the Solar System Internet. We have the ESA S-Track network of deep space stations, which provide a communication to all ESA missions in the solar system. It's also augmented by a network of commercial stations, partially deep space stations, but a lot of stations for communicating with Earth orbiting satellites. We also partner with NASA and the NASA ESA Mars Relay Network, where ESA spacecraft provide essential relay services to NASA rovers on the Martian surface. We have initiatives like Hydron, with the idea of basically providing glass fiber in the sky, aiming at terabit connectivity. We are currently setting up a demonstration system of 10 LEO satellites, each connected in a kind of ring fashion, each carrying 4 laser communication terminals, each also being able to communicate via optical communication back to Earth. There's a second element which also includes a MEO satellite, and there are ideas for also having a GEO node, which would also be able to provide connectivity into deep space. We have, of course, the Moonlight program. Moonlight program is about implementing communication and navigation constellation around the moon, similar to the NASA LCNRS program and JAX initiative. And there we work together with the other agencies to have a common standard, common specification called LunarNet. Marconi Lightship is, if you like, the extension of what we are doing around Moon towards Mars. Lightship 1 is now in phase AB, and this is the idea of having an electric propulsion tug spacecraft which will carry daughter spacecrafts and other assets to Mars. And once it provided the transport towards Mars, the idea is that Lightship will stay in orbit around Mars to provide communication and navigation services. So let's talk a little bit about the key technologies. We have identified three, let's say, technology pillars for solar system internet. Of course, one of those is disruption-tolerant networking for resilient and secure network communication. We have radio frequency and optical communication, communication to Earth, but also intersatellite links. And we have, as a third pillar, position, navigation, and timing for providing autonomous space-based position determination and navigation. So for communication, we see RF as a quite major technologies. Of course, there are further advancement possible, and we have a lot of research activities in this area. But we are also looking in application of terrestrial technologies for proximity links. For example, for surface networks, there we are looking to Wi-Fi and 3GPP technologies. There's a strong focus currently in optical technologies, as we see them as essential for high data rate communications. Optical communication between the NASA LEDI spacecraft and ESA's Esanya 1 station on Tenerife has already demonstrated more than 10 years ago. And very recently, in August this year, we were able to demonstrate optical communication over 300 million kilometers between the NASA Psyche mission and two observatories in Greece. So this could be a nucleus for future optical deep space communication capability. You see on the left the uplink beacon, which is basically pointing to the Psyche spacecraft 300 million kilometers away. And you see on the right what is seen in terms of uplink beacon on board of the spacecraft. On the upper picture, you see the Earth crescent, so where the sun is shining on Earth. You subtract this, you see the little dot in the middle, which is actually the 4 or 5 lasers you see pointing towards the spacecraft there. You might wonder what is the important data received from the Psyche mission. And of course, it's a cat video, a very famous video with a cat chasing a laser pointer. PNT, another important technology for us. Here we are looking not so much in constellations. Constellations can be part around the moon, can be around the Mars, but we are also looking very much into optical and RF ranging applications. Important here is that we need to have spacecrafts which can transition from one system to another while they are traveling through the solar system. Another area very important is this, and where we see a clear institutional role also for ESA, is a provision of reference frame and times for planetary bodies, starting with the moon now, but extended to Mars and other planetary bodies in the future as well. Now I would like to go a little bit in more detail regarding disruption-tolerant networking at ESA. We had a working group which identified mainly 4 groups of use cases. The obvious use case, human spaceflight and robotic exploration, where we see bundle protocol as the protocol for interoperable network end-to-end communication. Yeah, we are also part of the LunarNet initiative, which contains the DTN network communication service. Then space to ground communication. There we have several important aspects. We are looking into automatic retransmission of lost data, which is a high-performance reliability protocol, which is a successor to the LTP protocol, aiming at very high data rates. But we are also looking forward to use bundled protocol for autonomous end-to-end data distribution, in particular with less predictable downlinks, like we have, for example, with optical ground stations, where we might lose much more passes due to bad weather conditions, clouds, so we always have to plan for backups. Earth observation, we're looking forward as well in the application of bundled protocol because it will allow us to have less complex ground segments for high data rate downlinks. We are currently putting a quite complex system in place based on a distributed CFDP concept, where we have dedicated systems we deploy in ground stations and other systems we deploy at the control center. And it would be much easier if we can move to bundled protocol, because there we basically just need to provide bundled protocol nodes at the various locations. Finally, also we are looking into more resilient and robust communication, and especially in the case of constellations, we believe that with bundled protocol, we have the means to provide very robust monitoring and control of heterogeneous constellations. We have done quite a lot of work in the area of DTN-related implementations. ESA is maintaining its own bundled protocol ground implementation. We hope to have this open source very soon. It's a difficult process, unfortunately, for us. What is maybe special about this implementation is that we have a concept of convergence layer elements, which you can stack on top of each other to make a convergence layer adapter. We have elements, of course, for LTP, TCP, UDP, but also the space protocols, encapsulation packet protocols, space packet protocols, the various CCSDS frames, as well as, for example, space links and extension services, which are quite useful if you want to connect directly to a modem in a ground station, because this is typically providing SLE services, a file convergence layer, and others. In terms of client interface, we just redesigned our interface and have now a gRPC-based client interface. And I think this is quite interesting because I know there are several implementations which are also looking to gRPC, and there I hope that we can find some similarities, that we can provide a harmonized interface in some way to interface with various DTN implementations. We implement a lot of features. We have BPSec, we have custody transfer, compressed status reporting, quality of service, Anycast, and others. So we use this also as a kind of experimental implementation to look and research into new features. You have the DTN assembly, which is embedding the ESA bundle protocol implementation in a system which could be deployed as a ground station. So it has an MMI with the features we think are essential for an operator. It provides the ESA M&C protocol, which means it can be integrated with ground station management systems, can be fully automated with the means we have for automation today. We have an LTP implementation. We have an implementation of the high-performance reliability protocol in software and an FPGA implementation. There are ongoing activities to create a high performance, here we mean 10 gigabits per second or above ground station implementation. We're looking into potential reuse of HDTN and, for example, adding a gRPC client interface to that. And also there's an activity for a cloud native implementation. If you want to know more about this, talk to Rick, who has the talk just after me. We have a project to develop LunaNet compatible ground station equipment, which does not only include DTN implementation, but also potentially a modem. We have two ongoing study activities to create optical ground network test beds, which include DTN for data distribution. They also include a roaming interface for data distribution. They include also interface for scheduling and planning of ground station passes. This is even a little bit more than a kind of ground simulation or test bed, so we are already planning demonstration with real optical downlinks for next year. And we have a DTN network management study, which is about to be kicked off, where we will look especially into integration with the current operational practices. We have various standardization and study activities. We are looking into custody transfer and compressed status reporting. There is an CCSDS Orange book, which should be published, I hope, by the end of this year. Here we try to essentially 3 different things which are related. We introduce a mechanism to identify sets of bundle based on sequence numbering, and then we use this mechanism in bundle protocol extension blocks to request custody transfer and custody signaling. We also use the same mechanisms to identify bundle sequences in an extension block and request bundle status reporting. And this enables a lot of useful features, especially end-to-end services like gap detection, in-order delivery, bundle accounting, and many others. We have a BP quality of service CCSDS Orange book, which is almost finished, and I assume that Teresa was also present might talk a little bit about this. We recently defined a DTN interplanetary anycast scheme. There's an IETF personal draft out, so we try to have this standardized in IETF. We are working on the definition of DTN reference scenarios, which will come out as a CCSDS yellow book and a GitHub repository with the files describing these scenarios. This should allow testing of new features in a comparable way and should provide researchers a starting point to experiment with bundle protocol in realistic scenarios. We are working on BIBE segmentations. We had some work on what we call BIBOR, BIBE onion routing, and already looked also on DTN key management and key exchange. We also did some DTN demonstration activities. A long time ago, we already had the Meteron project where we demonstrated control of a robot pretending to be on Mars via the ISS. More recently, we did some OPSAT experiments, doing uplink, downlink with CFDP over bundle protocol, LTP, and space packets. What was interesting in these experiments that we had quite bad conditions regarding our passes. So we had lost passes, we had interrupted passes. We were still able to get files successfully down and up to the spacecraft, which provided a good test of the robustness of the protocols. By the way, there are new OPSATs coming up, OPSATs Oriole, OPSAT Volt, and I think registration is open at ESA for experiments on these spacecraft. We also did an experimentation and demonstration between ESA, NASA, and D3TN with Lunar Ice Cube. The plan was to receive data from Lunar Ice Cube at the ESA Kourou station. Unfortunately, communication with Lunar Ice Cube could not be established, so we did the next best thing. We used recorded data from Lunar Ice Cube, which we replayed with a spacecraft simulator at the station. So everything after the replay is really operational networks and really fully representative for a ground segment of ESA, NASA, and D3TN to how we would use it in a DTN scenario. This involved 4 different BP implementations, so it also shows the interoperability between all of those. Now I want to talk very briefly about ASSIGN, Advancing Solar System Internet and Ground. ASSIGN is a program focused on safeguarding the European role and interest in the global vision of the solar system Internet. It is committed to interoperability and international collaboration. It's a multi-directorate activity, and it's proposed as a new element under the Moonlight Program proposal for the Ministerial Council in November. For ESA, these Ministerial Councils are very important. They happen every 3 years, and they set basically all the budgets and the activities for the upcoming 3 years. So for us, it would be a big success if we are successful with this program proposal. It's very hard to start a new program at ESA. We are planning for a preparatory phase for the next 3 years and then go into gradual system implementations from 29 onwards. This is roughly what is contained in the program proposal for the ministerial. We had some preparation activities. We have run an SSI pre-phase A study, which looked also not only in the technologies, but also looked into the economic and strategic benefits of a solar system internet. We've run an SSI Pathfinder current design study, and we are going to have a phase A for this SSI Pathfinder. For the assign preparatory phase, we are looking into phase 0A studies, where we will look into the overall system architecture, the requirements, the upcoming missions, potential topologies, identify long lead items, identify development needs, look into the operational concepts. So this would be two bigger parallel study activities. We have a component we call the SSI enabler, where we want to support industry to build up operational DTN capabilities. But we also want to build up our own SSI reference facility, which would, for example, offer opportunities for DTN network testing, but also optical compatibility testing, PNT testing, potentially provide security services, and so on. And then there are a couple of technology de-risking activities in the various areas I've described before. As I already mentioned, at the beginning of this year, we had a concurrent design activity where experts for the different spacecraft subsystems came together in 8 sessions, and we designed a cislunar solar system internet pathfinder mission, now called SSI Node 1. We had the following mission statement. The SSI Pathfinder will be the world's first mission to demonstrate reliable routine operations of the cislunar optical trunk link. And this is quite important to me. So we have seen all these optical demonstrations, but to bring optical communications into operations, we need to prove that we can reliably return data each day over a very long period of time, and that we can operate these links in an automated fashion like we do for RF links. It would be the first ESA missions to use disruption-tolerant networking operationally. It will demonstrate technologies for deep space PNT and prepare the provision of lunar reference frame and lunar reference time. So I put the kind of technical data we came up with. It would be a small SAT. We would be able to provide up to 5 gigabits optical downlink from cislunar space, either direct to Earth or to a height 1 geo extension. We would have a reprogrammable DTN implementation on board. We would be fully LunarNet compatible. We would do a lot of laser ranging for PNT purposes. So the SSI Node 1 Phase A ITT went out, I think, now 3 weeks ago. So we will continue this activity. And of course, we hope to get also funding for this mission in the Ministerial Council. So to summarize, ESA is fully committed to the vision of the solar system internet. For us, it includes optical RF communication, but also navigation services. The SSI shall be based on public standards to enable interoperability and international cooperation. We have various ESA activities which contribute to a solar system internet. So a sign would be there to provide an additional level of coherence and synergies among these various activities. Optical communication, disruption-tolerant networking, and deep space PNT are key activities, key technologies for us. The ASSIGN program aims at providing the European contribution to the solar system internet. We are planning for a preparatory phase from 26 to 28 with system studies, technology de-risking, and SSI enabling activities. And we will continue with the definition of the SSI Pathfinder mission to cislunar space to demonstrate routine operations of an optical trunk link, space internet working, and deep space PNT. Thank you.